Hi, I'm Kate Bricker, and this is Physics 2211, Lab 3, Black Hole Orbits. So just to introduce this lab, our purpose of this lab was, we had two different parts. The first part was to find the mass of the black hole by analyzing the star, and then the second part was to try to put our spaceship in a figure 8 going around the planet and the moon to get to the star. So our system for this was the spaceship, and we had lots of surroundings, including the moon, the sun, the earth, or the moon, the sun, the planet, and star. And our methods were we just did this using code. We didn't have an in-person lab to do this. So speaking of the physics of this, our fundamental idea is using Newton's second law, which is force equals mass times acceleration. But for this experiment, which you'll see later in the code, we split this into parallel and perpendicular forces in order to find the velocity and the change of momentum of this force. And we also used the equation of gravity, which is F equals g m1 m2 over r squared, to find the laws of gravity. And you can see later in order to find the mass of the star, we rearranged this equation to isolate m and use the force and gravity and the distance to find the mass of the star. So speaking of the first part of the experiment, you can see our code here. We start with the initial conditions of our star and our gravity and our time without changing that. And you can see that this is updating the x and y at every time of plus t. And then for this, we calculate the momentum of the experiment by using the perp and perpendicular forces. So you can see we're trying to calculate the perpendicular force here, and then we calculate the parallel force, and then to find the black hole, we do what I said by taking the force times the star's position over the mass to find that total mass of the star. And we do this at every point around the graph and to find the mass of the star. So like I said, here you can see each point of the screen line is a different place where we take that calculation of the distance from the star in order to find the mass of the star. And we found the mass of the black hole, the mass of the black hole was 7.3 times 10 to the 32nd. Going back to the second part of the experiment, we were trying to find how we wanted to put our spaceship into a figure 8, both around the planet and the moon, and this was by trial and error. You can see that our conditions of gravity, mass, and time were the same, but what we changed was the velocity of the x and y direction. So you can see that we found this by just finding the force of the moon and finding the force of the spaceship and applying Newton's second law, and updating the position based on these velocities of the moon and the ship to find that distance. So as you can see here, we didn't end up finding figure 8 perfectly, but our planet didn't crash, and you can see this motion was more of a circle than a figure 8, and you can see that our speed of our moon was about 2.4 times 10 to the 4th meters per second, and then the period was about 64 hours. So to discuss this, I'm going to skip to the end actually. What are the errors in our experiment? Well, we're just approximating this, so it's not really exactly perfect. We don't have all the forces involved in our experiments, which makes our experiment not very accurate to real life situations, but our experiment is pretty accurate to a lab simulated experiment. So what does this mean? We are asking how is net force of the parallel and perpendicular components different from the rate of change of momentum of its parallel and perpendicular components? Well, this is just a trick question because they're the same. But rate of change of the momentum is easier to calculate. So that's why we calculated the parallel and perpendicular forces of that change of momentum in order to find the total net force. So what if we wanted to predict the motion of the entire system? What would we need to include in our model? So if we wanted to have the entire system, we would need the forces of the moon, the black hole, the planet, and the star. We would all those forces, all those masses, all of it. And then what would be the dominant interactions, or would it all have less equally? So the dominant interactions would determine based on the force, and it really depends on the mass and the distance.